Okay, everybody, so in this video, we're going to be talking about equivalent capacitance, okay? So in order to solve equivalent capacitance problems, one of the most important things that you have to take into account is that finding the equivalent capacitance is basically works in the opposite way of resistors and inductors, okay? And we can show this in the following manner. Let's say we have three capacitors in parallel, right? And this extends to more than three as well. Let's say we have C1, C2, and C3, right? They have the same beginning and end points, right? Same beginning point here, same beginning point here, same beginning point here, same end point here, same end point here, same end point here, right? So they basically have the same voltage drop across them, right? That's what in parallel means, all right? And in case you're still confused, like how is this point the same as this point? Remember that this is all one piece of wire, right? And because it's one piece of wire, you can think of it as one big node, okay? So as one big point per se, okay? So you can think of it that way as well. And the same thing here. They all have the same endpoints as well because this point is essentially the same as this point and it's basically the same as that point because this is just one big piece of wire and it can be thought of as one big node or one big point, okay? And now when we have capacitors in parallel like so, we just sum up the individual capacitance values. So in this case, CEQ would be equal to C1 plus C2 plus C3. And this is basically the opposite of what we would have if we had resistors in parallel or inductors in parallel. If it was a resistor in parallel, if it were three resistors in parallel, we would use 1 over R1 plus 1 over R2 plus 1 over R3 and find the inverse of that. Alright, so that's just one example of how they work in the opposite manners. Alright, now let's go to the series case. So here we have three capacitors in series, okay? So let's just imagine there's current, or more specifically, let's say there's displacement current, right, flowing through these three capacitors, okay? And because there's only one path that current can take, because let's say this would be one node between C1 and C2, current can only take one pass. There's only one node between C2 and C3, current can only take one pass, right? So because current can only take one pass through these three capacitors can be seen as in series, okay? Now, in order to find the equivalent capacitance in this case, for these three capacitors in series, it would be 1 over C1 plus 1 over C2 plus 1 over C3, and you find the inverse of that to the minus 1, okay? That's what inverse means. And another way of just saying that would be 1 over, and then here you have 1 over C1 plus 1 over C2 plus 1 over C3, just what we had here, okay? And it just continues if you have two or more than three capacitors in series and in parallel, the formulas still stand, okay? So now that we have the basics out of the way, let's go to a more concrete example. We have this example here, all right? So at first it can seem a little bit intimidating, but after simplifying the circuit, which is key, whenever you have a circuit like this, the most important thing you have to take into account is to just simplify it, and then you will see, hey, it's not that bad, okay? So in this example, we have two terminals, terminal A and terminal B, and you want to find CEQ, or the equivalent capacitance, across these two terminals, okay? So here we have the capacitor values, and so capacitors are normally in units of microfarads, okay? Because a farad is a really big unit, so you use microfarad or picofarads, 1 times 10 to the negative 12 farads, okay? But in this case, it's all going to be microfarad to make the numbers a little bit easier, okay? No conversion factors, basically, okay? So how do we start this problem? How do we tackle it? Well, first of all, we got to identify which capacitors are in series and which ones are in parallel, okay? So just starting from terminal A, we have the 2 microfarad capacitor, and we can see that these two capacitors, the 3 microfarad and the 1 microfarad, these two are in parallel. And why is that so? Because they have the same beginning point here, and they have the same end point here, right? The 3 microfarad begins here, it ends here. The 1 microfarad can be thought of as beginning here and boop, ending here. Alright, and if you're still confused, just remember this is one big piece of wire, one big node. So if you think of this as a point, these two are basically in parallel, they have the same voltage drop across them. Alright, so we're going to redraw that in a little bit, but before we get to that, you can also make a similar comparison between the 10 microfarad and the 6 microfarad capacitors here. Right? Same voltage drop between both of these, same beginning point, same end point, right? Now you might be thinking, well, they're the same endpoint, but what about this thing right here, right? I mean, this is not just one piece of wire. There's a capacitor right there, right? So how can we say that these two are in parallel? Well, you might be confused at first, but we're also going to redraw this thing over here, and you're going to see that these two capacitors are actually in parallel. Okay, so let's get to redrawing this. Let's see here. So we're going to have terminal A over here, and I'm going to drop the units to make our lives just a little bit easier. Okay, so you're going to have this 3 microfarad here. You're going to have the 1 microfarad here. Note here, you're going to have the 10 microfarad there. Okay, so let's see here. You're going to have... Alright, so this is where it gets a little tricky. Alright, so let's say we're here. Okay, so once you pass the 6 microfarad capacitor, you can either go through the 4 microfarad capacitor and go to terminal B, or you can go through the 2 microfarad capacitor and through the other 2 microfarad capacitor, and you can go through terminal B. Alright, so what does this imply? It implies the following. It implies this, okay? And I'm going to walk you through it to make sure it makes some sense, alright? There we go. Perfect. Okay. Let's see so you can see it a little bit better. Alright. So, 2 microfarad capacitor, and we agree, let's connect the dots here, right? We agree that these two are in parallel, right? The 3 microfarad and the 1 microfarad, like over here, in parallel. 10 microfarad, 6 microfarad, also in parallel, right? But what about this weird triangle here? Well, I've redrawn this weird triangle over here, okay? So let's just walk through it. You pass the 6 microfarad capacitor, you go through the 4, and then you go to terminal B, right? It's the same case here. You pass through the 6 microfarad, you go through the 4 microfarad, and you go through all this wire all the way to terminal B, okay? And here, or you can also pass through the 6, then the 2, and go to terminal B. Same thing here. You pass through the 6 microfarad capacitor, then through the 2, and all the way to terminal B, right? So it's basically the same thing. So what do we have to do now in order to further simplify the circuit? Well, first of all, we should probably focus on this box over here, okay? Now, and this is where our previous general rules also come in handy, okay? So let's continue to simplify the circuit. Actually, let me see if I can simplify it here. The drawing might be a little smaller. Hopefully, you'll still be able to see it. So we got 2, we got 3, we got 1 over here. Actually, we could combine these right now, right? Because these two are in parallel, and based off of our general rules, right? If they're in parallel, you just add them like so. So as a result, we can just combine these straight away. 3 plus 1 is equal to 4, so it would form a 4 microfarad capacitor in terms of equivalent capacitance between those two capacitors, okay? So let's see, we have the 10 over here. We got the 6 over here. So let's start simplifying, right? These two right here, they are in series, right? For capacitors in series, let's work the math out here. The CEQ would be equal to 1 over 2 plus 1 over 2 inverse, right? Just like in our general rules. In series, 1 over C1 plus 1 over C2 plus 1 over C3 inverse, right? Same thing as that. And in this case, we only have 2 capacitors in series that we're focusing on right now, so that's what we're going to do. I'm just going to try to work out the math from A to Z, so 1 over 2 plus 1 over 2 is just 1, right? And the inverse of 1 is just 1 over 1, which is just 1 microfarad, so pretty simple. Okay, so we have, let's say we have the 4 here, and we have the 1, okay? All right, perfect. So we simplified it up to there, okay? So now what? We can continue to simplify this in the following manner. The 4 and the 1 microfarad capacitors are in series, so we just add them, right? 4 plus 1 is equal to 5, right? How many fingers do you have? How many fingers do you have? You got 5 fingers, okay. So let's continue to simplify the circuit, okay? So you have terminal A over here, you have 2 microfarads, you have the 4 here, you got 10, 6, terminal B over there, 4 plus 1 is 5, like so, okay? So it's getting a little bit more simple, alright? So we have this basically, and also just a very minor thing, so right here, I had, after this box, I had some wire coming down, and then after that, I kind of cut and I had this wire coming down here, and it seems like I kind of cut the wire off. I mean, it doesn't matter how you reconfigure it. I could also draw it in this manner, in the end it's just wire, right? So, but I'm just gonna keep it like so, okay? Because in the end it's just wire, it's basically the same thing, okay? And terminal A and B should basically be at about the approximate same level. Again, just some minor things you should take into account, okay? So now we have the 6 and the 5 microfarad capacitors, right? So what we're going to do now is the following. We're going to combine these two, and these two are in series, okay? So the equivalent capacitance would be 1 over 6 plus 1 over 5 inverse, right? And you can just plug that into your calculator, right? Normally your professor should allow you to use a calculator unless he or she is a mean professor, but we're just going to simplify it. It'll be about 2.73 microfarads, okay? So we can continue to simplify this in the following manner over here. So you got terminal A, 2, 4, 10, 2.73, not the most beautiful number, but it should work at the end. Alright, just combine these two. You have A, 2, 4, 12.73, terminal B. Okay, so at this point you're going to have 3 capacitors in series. Alright, so therefore CEQ would be equal to 1 over 2 plus 1 over 4 plus 1 over 12.73 inverse, and plugging that into the calculator you should get a number that is obviously a decimal value, but it should still work out well in the end, okay? You get about 1.21 microfarads, okay? So this is just one worked example of equivalent capacitance, and it also shows you how important it is to redraw your circuits, right? So hopefully with this example, it'll help you in your future endeavors within electrical engineering or just a basic intro to circuits class, and I hope this example helped you. Thank you for watching.